welcome to the deep dive. Ever stop and think, what actually makes your computer do things?
Yeah, it's something we take for granted.
Totally. So today we're diving into the operating system, that fundamental software layer that manages everything.
The hidden conductor, as you put it.
Exactly. We're digging into the Wikipedia entry on OCs, our mission, to pull out the really important stuff, what it is, what it does, the different flavors, a bit of history, the key part.
But without drowning you in technical details, keep it clear.
Right. So let's start with the basics. What is an OS, really?
Well, the definition given is the layer of software that manages a computer's resources for its users and their applications. Think of it as the ultimate manager.
Okay, managing resources, like what?
CPU time, memory space, making sure applications play nicely together. It's basically composed of the kernel, that's the core part that's always running, and then other system programs.
Got it. So this manager, it has, like, main jobs.
Yep, three main purposes, really. One, allocating those resources, as we said.
CPU memory.
Right. Two, providing a simpler way for programmers to interact with the hardware, an abstraction layer.
So they don't need to know every hardware detail.
Exactly. And three, offering common services. Things like network access, talking to the hard drive, stuff lots of applications need.
Okay, let's unpack that resource management bit first. It's dividing up the computer's power.
Pretty much. It ensures one program doesn't just, take over everything and starve the others.
Like a traffic cop for the CPU.
Yeah, that's a good way to think about it. And it also isolates applications, keeps them in their own little sandboxes.
For protection, like if one crashes.
Exactly. Protects against errors, security issues too. But importantly, it still allows them to communicate when needed, carefully.
Okay, walls with secure doors.
Mhm.
Makes sense. Now, that hardware abstraction making things simpler for programmers, how's that work?
It's actually quite clever. Instead of a program having to deal with, say, the exact physical location of memory chips,
Which sounds complicated.
it is. The OS provides an interface, and it often uses virtualization. Think virtual memory. It makes the computer seem like it has more RAM than it physically does.
How? By using the hard drive.
Often, yeah. It swaps bits of data back and forth. It's like juggling gives the illusion of holding more than you actually are.
Smart. Okay, and the third thing, common services, like internet and file access.
Right. Providing standard ways for applications to do common things, like saving a file or sending data over the network. This is actually a huge part of the OS code.
And it means an app can run on different types of hardware without needing a total rewrite, right?
Precisely. It creates consistency. Now, we should probably talk about the different types of OCs because there isn't just one kind.
Good point. Like multi-computer ones for cloud stuff.
Yeah, those are for systems with multiple CPUs, each often with its own memory. Think huge data centers. The big challenge there is making them communicate efficiently without too much overhead.
Okay, and distributed OCs, how are they different?
Distributed systems involve computers connected over a network. They might be spread out geographically, each potentially running its own OS. You often need extra software, middleware, to make them act like one coherent system.
Right, coordinating across distances. What about the tiny ones? Embedded OCs.
Ah, yeah. Those are designed for specific devices, IoT gadgets, appliances, maybe your car's infotainment system. They usually don't load user-installed software.
So simpler, more focused.
And often tiny. We're talking potentially less than 10 kilobytes. Some for smart cards are even smaller. Embedded Linux, QNX, Tiny OS, those are some examples.
Wow. Okay, then there's real-time OCs. What's special there?
Timing. They guarantee that a task will be processed by a specific deadline, crucial in some industries.
Like manufacturing or airplanes.
Exactly.
Cool.
That's hard real time. Missing a deadline is a failure. Then there's soft real time where occasional misses are okay. Think multimedia streaming, maybe your smartphone.
Got it. Precision matters more in hard real time. What about hypervisors? We hear that term with virtual machines.
Right. A hypervisor is basically an OS designed to run other OACs. It creates and manages virtual machines. Super useful for development, testing, running different systems on one machine.
Like having multiple computers inside your one computer.
Pretty much. And finally, there's a more specialized type called a library OS or libOS.
Library OS. How's that work?
Instead of a big kernel, the OS services are compiled as libraries directly into the application. It creates something called a unikernel.
So the app is the OS, in a way.
Sort of. Very efficient, no separation between app and kernel space, good for specific high-performance or embedded tasks, cuts down overhead.
Interesting. Okay, quick history lesson then. Where did this all start?
Way back, early computers didn't really have OACs. You programmed them very directly. Plug boards, machine code,
Hmm.
very manual.
Sounds tedious.
It was. Then mainframes got rudimentary systems like IBM's OS 360 in the 60s. That was a big deal. Compatibility across different machines and multi-programming, running multiple jobs at once.
Okay, that's starting to sound more familiar than time sharing.
Right. Multi-CS was a key project there, kind of a precursor to cloud ideas. And from that came UNIX.
Which is huge, right? Lots of modern OCs trace back to UNIX.
Absolutely. Linux, Mac OS. Then the 80s brought microcomputers. CP/M was big early on. Then MS-DOS took over the IBM PC world.
And then came the pictures. Graphical interfaces.
Yep. Apple Macintosh made GUIs popular, then Windows followed and eventually dominated the desktop. And now mobile is largely Android, which itself is based on the Linux kernel.
So it's been this constant evolution towards more power, more multitasking, easier interaction.
Exactly. So what are the key parts of a modern OS? We mentioned the kernel.
The core brain manages memory, hardware access, keeps things secure, runs in a special privileged kernel mode.
Right. Then there's program execution. When you run an app, the OS creates a process, gives it resources, loads its code, and kicks it off.
Okay, and interrupts, what are they?
Interrupts are signals to the OS that something needs attention right now. Could be hardware like data arriving from the network, or software like an error, or you pressing Ctrl+C.
So it's how the OS reacts quickly to events.
Precisely. It pauses what it's doing, handles the interrupt, then resumes. Memory management is another huge one, especially with multiple programs running.
Got to keep them from messing with each other's memory.
Yep. Early systems where cooperative programs had to behave. Modern systems use memory protection enforced by the kernel and hardware, often using techniques like segmentation or paging, and virtual memory, which we talked about.
So the illusion of more RAM using disk space. What about doing multiple things at once? Concurrency.
That's usually handled with threads, smaller units of execution within a single process. Most OAs use preemptive multitasking, where the OS actively interrupts threads to give others a turn.
Keeps things responsive. And storage, the file system.
That's the abstraction for your hard drive or SSD. It gives you file names, folders, organizes everything, controls access, handles caching, makes storage persistent and reliable.
And security, obviously, is critical.
Absolutely. Protecting users, data, confidentiality, integrity, availability. OCs use isolation, check permissions, try to follow principles like least privilege. Different designs like microkernels might offer different security trade-offs.
But vulnerabilities still exist.
Oh, definitely. Buffer overflows, hardware flaws. It's a constant battle. And finally, the user interface, the UI.
How we actually use the computer. Command line or graphical windows, icon.
Wait, that's our window into everything the OS is managing underneath.
Wow. So yeah, operating systems really are the unsung heroes. So much complexity managed behind the scenes.
It's quite amazing when you think about the journey from those early direct programmed machines to what we have now. Virtualization, complex security, managing countless tasks.
It really makes you appreciate that intricate dance of resource allocation, protection, abstraction, happening constantly on your phone or computer. So here's something to ponder. What other fundamental layers of technology are quietly shaping our experiences every day, maybe in ways we don't even realize?
Good question to leave folks with.
Thanks for diving deep with us today.